Okay. So you guys might have noticed last lecture, we did not talk about sum statements, and that's because these are a bit more complicated. So this thing's driving me nuts. It wants to do that pencil thing, but whatever. So let's take an argument using some sum statements. So remember, we're going to set this up the same way we always do. All right. All A are B. How are we going to model that? All A or B, well, we black out everything that is in A, but not B. All right, easy, easy, easy. But now what do we do with our sum? This is where it gets hard because we want to show that an argument's valid. And so I think the way to do this is when you're thinking about sum, you want to imagine that you are playing a game. And so you imagine that the person you're playing with wants to win. She wins if she can show a way that your premises are true and your conclusion's false, right? Your argument's not valid. So we have all A or B. A is blacked out. Now we have some C or A. So she can only put, she has to put where C and A overlap, and she can't put in this black space, right? So she has to put her X here. Well, let's look at our final one, some C or B. Well, lo and behold, that's true because there is something in this space here where C and B overlap. Sorry, I'm blacking it out, I guess, with that. Let me erase that. I'll erase my whole diagram, right? Sorry, we're blacking out our A except where it overlaps with B. So some C or A, we have to put it here where A and C overlap. And my point is that, you know, wherever we drop this in the C that's open to us, we have to do it where it overlaps with A. Well, the only place open is where A overlaps with B. So there is going to be something in this space here, some C or B. That just means that there's an X where B and C overlap. With these premises, that's the only way to draw this, right? Let me give you another one though. Now we're with blue, but whatever. All right. All A or B, some B or C. So our conclusion, some A or C. And again, A, B, C. So, and you guys will notice I'm always putting the sum statement second. I will talk about that. But the reason is it makes it a lot easier to use Venn diagrams for sum statements. If you always, you should put any statement that has all or no, your universal statement. If there's any of those, they should go first. If there's a sum or a sum are not, they should go second. This will make your life a lot easier to use Venn diagrams to model validity. All right. All A or B. All right. So we have to black out all of A. Now we look at our conclusion, right? Our conclusion says some A or C. If there is something in this C space where A and C overlap, then it's a valid argument, right? If by the time we are done with our premises, we have to put something there, then our argument's valid. Let's erase it because we don't know if it's there, right? So we say some B or C. And we think of ourselves as playing a game, right? We are playing this with a hostile player. She has to make this move. She has to put something where B and C overlap, but she wants to do it in a way that our conclusion is false. Can she do that? Can she put an X where B and C overlap that doesn't land where A and C overlap? Well, of course she can, right? She has this space open here to put her X. She does not have to put it where A and B overlap. The argument is not valid. Van Cleve doesn't do this, but you will make your life a lot easier if when you have some statements, you always put them second if there is an all or no statement. It'll be a lot easier to use Venn diagrams. You can do this like this. Life will be easier, right? So is this valid? No, because there are ways she can put her X in all sorts of places that aren't in this overlap, right? I mean, look, there might be something in the overlap, but if we picture a hostile player, she doesn't have to put it there. She's not forced to, right? Not a valid argument. Let me give you guys another example. All right, draw our Venn diagram again. A, B, C, right? always start with our all or no statements, all A or B. Well, how do we model that one? We black out every part of A that does not overlap with B. That's what we do. Show that there's nothing that can go in A that doesn't also go in B. All right, check. Now, because some statements are more complicated, we will look at our diagram. Some C or not B. Well, we have to draw something in C where C overlap, where that's not in B. Is there any way, we look at our conclusion, some C or not A, is there any way that we could draw outside B, but also put it in A? No, there's not, right? This part here, where C and A overlap, is blacked in. Nothing can go there. Whatever we put in C, our opponent can put it wherever she wants. Wherever she puts it, it's always going to be outside A, right? No matter where she draws the X, there is going to be at least one X, at least one thing that is in B and is not, or sorry, is in C and is not in A. Sorry, I erased my whole C there, but you guys get the idea. Oh, now we're back to black, right? All right. So hopefully you get an idea how we use these some and some are not statements, right? It really helps if we always start with the all or no, and then we use our some statement, right? What do we do if we have two some statements? Well, honestly, doesn't really matter because two some statements don't prove very much, at least not in, you know, categorical logic. Let me erase that. So hopefully you guys are getting an idea. With the some statements, that's when it's helpful to think of this as a game. You are playing with a hostile person who does not want to grant your argument. She wants to think of a way where your premises are true and your conclusions false. If she can do that, if she can put an X where your conclusion says there shouldn't be an X, the argument's not valid. It doesn't work. Some statements are more complicated. Some and some are not statements are more complicated than all or no statements because when you fill them in, you also have to look at your conclusion. It's not just a one-step thing. And you have to try to think, well, is there a way to do what the premise says where the conclusion ends out false? That makes them a little more complicated, but with a little practice, they're really not complicated. Now, look, as I said, if you have an all or no statement, you should put it first. For purposes of validity, you know, it doesn't matter. This is a valid argument. This is also a valid argument. But it will be way easier if you're doing a Venn diagram to draw it for the second version here than it would the first. So if you're using Venn diagrams, you are going to make your life a lot easier if you put the universal statement first and any particular statements you have, whether negative or affirmative second, that'll make it a lot easier to draw the Venn diagram, right? Because then we have, you know, no B or C. We black out everything here where B overlaps with C. That's an easy thing to do. Then we look at our conclusion and our second premise, sum A or B. Well, we have to put this X here where A and B overlap. If we do that, are we going to have something in A that's not in C? Well, yes, we will. There's no way she could draw this where there's not something, she has to put the X in a place that's in A and not C. So this is a valid argument. Anyway, I hope the basic idea is making sense to you guys. We will practice a lot more with using Venn diagrams to prove validity in class. As long as the basic idea makes sense to you guys, then I think we're in good shape. All right, so that's really it for the stuff to at least start with categorical logic and Venn diagrams. The basic ideas, we will do a lot of practice to apply these ideas.